Welcome back to the deep dive. Today isn't just another standard science topic. We are stepping directly into the ring to fight the absolute heavyweight champion of unresolved problems in physics.
Oh, yeah. It's the big one.
Right, and I'm not talking about dark matter or the expansion rate of the universe. Those are, massive headaches in their own right. I'm talking about the structural fracture at the very bottom of reality.
A century-long divorce.
Exactly, the separation of general relativity and the standard model.
Yeah.
I mean, we all know the headline you see in every science magazine.
Yeah.
Gravity describes the stage, quantum mechanics describes the actors, and they completely hate each other.
They refuse to speak the same language.
But I want to start by clarifying why this is such a nightmare, because I think the popular science explanations, they often miss the technical brutality of the problem. It's not just that one is smooth and the other is chunky. It's a crisis of what physicists call background independence.
That is the crux of it, yes. General relativity is, by its very nature, background independent. The geometry of space-time, the metric tensor, is a dynamic variable. It evolves. It reacts to mass and energy. There is no fixed, rigid grid underneath it all.
Right.
But the standard model, which is built entirely on quantum field theory, absolute, requires a fixed background to even function. It usually uses flat Minkowski space just to define its basic operators. It needs a rigid stage to calculate probabilities.
Right, so when you try to merge them, when you try to actually quantize gravity, you're essentially trying to turn the stage itself into an actor.
Exactly.
You try to treat the metric as a quantum field, you linearize it, and you calculate perturbations, and that's where the math just completely explodes in your face.
It does. You get what we call non-renormalizable infinities. You try to measure a simple distance, but your ruler is suddenly subject to quantum uncertainty, and it essentially vanishes into a haze of infinite probabilities.
Right. It's not just a polite disagreement. It's a fundamental language barrier. Differential geometry and quantum field theory are speaking mutually unintelligible dialects. And, we've spent decades trying to force them together.
Decades. And thousands of careers.
String theory adds extra dimensions to give the math room to breathe. Loop quantum gravity tries to discretize the background right out of the gate. But today we are looking at a stack of source material that proposes something completely different.
Yes. We are looking at closure physics, or, to use the formal terminology from the papers, the closure consistency of relational transport.
Which is a mouthful.
It is. But the claim here is incredibly audacious. It suggests that we don't actually need to glue gravity and quantum mechanics together at all. It suggests they were never separate to begin with.
That they're two sides of the same coin.
Not in a poetic sense either, in a highly rigorous variational sense. It posits that they are complementary stationarity conditions of a single underlying principle.
A single principle about closing loops. And honestly, this is what completely hooked me when I was reading the sources. The idea that the entire zoo of particles, all the fundamental forces and the curving of space-time itself are just the universe's way of balancing its checkbook when information moves in a circle.
It's a geometric unification, but it starts much deeper down than geometry usually dares to go. It starts with the absolute bare concept of relation.
Okay, so let's unpack this for everyone listening. Our mission on this deep dive is to verify if this dual bivector framework actually holds water.
Yeah.
We're going to walk you through the derivation, literally how you get Einstein's field equations and the Yang-Mills equations from just one rule.
And we also need to delve into the 138 cluster.
Yes.
Because that part claims to explain why the standard model has the specific gauge groups it does, which is huge.
And that part is particularly fascinating to me because it moves from just describing nature to actually predicting the architecture of nature based on, stability costs.
It moves from describing what is to explaining why it must be.
Right. But before we get to the flashy results, we have to understand the foundational building block. The source material begins with a mathematical proof called the minimal generator theorem.
Right.
And it essentially argues that if you want to build a universe from scratch, you can't start with particles. You can't even start with space itself. You have to start with relation.
It requires a total ontological shift. Standard physics almost always assumes a manifold, a space already exists, and then we just drop fields and particles on top of it.
Like placing pieces on a chessboard.
Exactly. But this framework strips all of that away and asks a very fundamental question. What is the minimal mathematical object required to describe a relationship between two completely abstract states?
And the intuitive answer for most of us would be a vector, right?
Yeah.
An arrow, point A to point B. That's literally how we learned physics in high school, displacement.
It is intuitive, but it turns out to be mathematically insufficient for a universe like ours. The source formally proves that vectors are degenerate. They are too simple to generate a complex physical reality.
Because they commute.
Precisely. Vectors are abelian. If I displace a system by vector A and then by vector B, the end result is A plus B.
Right.
If I reverse the order and do B then A, the result is B plus A. They are perfectly identical. The difference between the two paths is strictly zero.
So a universe built solely out of vectors it'd be this perfectly flat, commutative, memoryless slide. Nothing would stick. Nothing would twist.
Yes. And we know for a fact our universe isn't like that. We have non-abelian gauge forces. The strong nuclear force, for instance, involves gluons that actually interact with themselves. The order of operations in our universe absolutely matters.
Right, the universe has twists.
It has twists. So to encode that non-commutative structure at the very base level, you need a generator that is sensitive to order. A vector is a rank 1 tensor. It's just too low grade.
You need to climb a step up the mathematical ladder.
You have to go up a step in the Clifford algebra hierarchy. You need a grade 2 object. You need a bivector.
Okay, so for everyone listening and trying to visualize this, a bivector isn't an arrow. It's an oriented plane segment. It represents an area with a specific direction of circulation. It essentially encodes rotation.
And rotations are fundamentally non-commutative. Think about holding a book in front of you. Rotate it 90 degrees around the x-axis, then 90 degrees around the y-axis. Take note of how it's facing.
Got it.
Now start over and do it in reverse. Y-axis first, then x-axis. The book ends up facing a completely different direction.
Right. The order changes the outcome.
That rotational non-commutativity is the seed of complexity required to generate physics. The dual bivector is the mathematically minimal object that captures this essential property.
So the core argument here is that we aren't building reality out of tiny Lego bricks. We aren't starting with particles, but out of these fundamental twist relationships. The dual bivector is essentially the atom of connection.
Yes. The formal term in the papers is the generator of relational transport.
Which brings us to the actual engine of this entire theory. Transport. And this feels like we're stepping squarely into gauge theory territory. We're talking about moving information along a path.
We are talking about holonomy. That's the technical term you'll see in differential geometry. Imagine taking a geometric object, maybe a vector, a spinor, or a coordinate frame, and transporting it along a closed loop in this relational manifold.
This is what the source calls the loop test.
The loop test. You start at point P, you traverse a path that circles all the way back around to point P. The fundamental question of physics, viewed through this lens, is simply this. When you return to P, is the object identical to when it left?
And if it's a perfectly flat, trivial space, it comes back completely unchanged. The loop is closed perfectly.
Yeah.
Identity equals identity.
Correct. But if there's physics happening, if there's a gravitational field, if there's an electromagnetic field, then the object comes back changed. It comes back slightly rotated or phase shifted. There's gap, a closure defect.
And this is where the terminology of the framework really shifts our perspective. Because in standard geometry, we just call that gap curvature. In quantum gauge theory, we call it field strength, or F mu nu. But this theory unifies them both under the single term closure defect.
It's a incredibly powerful reframe. It says that the forces of nature and the curvature of space-time are just measurements of the universe's failure to be holonomically consistent. The field strength literally is the density of that closure defect.
Okay, so we're picturing a universe completely full of these tiny defects. Things aren't closing perfectly as information moves around. Now, what does the universe actually do about it? Because this is where we hit the principle of closure consistency.
This is the action principle of the theory. In physics, we almost always derive the equations of motion for a system by minimizing something called an action. This theory proposes a very specific, very foundational functional, the closure consistency functional.
Which is, roughly speaking, just the sum of all these microscopic closure defects squared, right?
Mathematically, it's the integral of the inner product of the field strength with its Hodge dual. But conceptually, yes. The universe constantly tries to arrange itself to minimize the total amount of closure failure. It desperately wants to be consistent. It wants those loops to close as tightly as possible.
And this is the absolute moment of truth for this whole idea.
Yeah.
The source claims that if you take this one single rule, just minimize the closure defect, you can mathematically derive both the standard model and general relativity. But the trick, and I really love this part, the trick is what you choose to vary in the equation.
Exactly. It's a bifurcation based entirely on the variable of differentiation. We have two fundamental conjugate ingredients in this geometry. We have the fiber, which is the connection, and we have the base, which is the metric or the frame field.
Okay, let's walk through this carefully. Let's take path A first, the fiber variation.
So imagine we hold the background geometry completely fixed. We aren't stretching or warping space at all. We are only allowed to wiggle the connection, the internal rule that tells us how to transport phase or internal symmetry from point to point.
Okay.
We vary the action purely with respect to that connection field.
And when you crank through that calculus, doing the integration by parts, applying the trace properties, what actually pops out of the math?
You get the covariant derivative of the dual field strength equating to 0.
Which is the Yang-Mills equation.
It is the absolute foundation of the Standard Model. It describes exactly how the electromagnetic, weak, and strong fields behave and propagate. They are the mathematical result of the universe trying to minimize the closure defect by adjusting its internal relationships, the fibers.
So all the quantum gauge forces are just the system's way of handling fiber stress.
That's a great way to conceptualize it. Yes. Now let's look at path B. We go back to the exact same starting functional, the exact same integral of the defect squared, but this time we lock the connection down.
We don't wiggle the internal rules this time.
No. Instead, we wiggle the substrate itself. We vary the action with respect to the frame field, or the background metric.
We're stretching the canvas.
Precisely. And when you perform that variation, the math forces a completely different geometrical term to emerge to balance the equation. You get the Einstein tensor balanced directly against the stress-energy tensor.
You literally derive the Einstein field equations.
You do.
That is, structurally that is stunning. Gravity isn't a separate, grafted-on force. It's the exact same drive to minimize the exact same defect, but achieved by warping the base instead of the fiber.
It beautifully resolves the dichotomy we started the deep dive with. Why do gravity and quantum forces seem so fundamentally different? Because they are conjugate responses to the exact same underlying stress. Gravity is the base response. Gauge forces are the fiber response.
It really reminds me of how a physical material responds to heat. You can either conduct the heat, which is an internal flow of energy, or it can physically expand, which is a geometric spatial change. Both are just different responses to the exact same energy input.
That's a very apt analogy. The closure defect is the thermal stress in your example. Yang-Mills gauge dynamics is the conduction. General relativity is the expansion.
But, and this leads directly to the most immediate objection anyone is going to have, if they're essentially two expressions of the same thing, why do they look so completely irreconcilably different in our universe?
In what sense?
Well, gravity is incredibly, almost incomprehensibly weak. I can easily lift my coffee cup against the gravitational pull of the entire planet Earth. And gravity is smooth, continuous. While gauge fields are quantized into discrete, violent little particles, why does this single principle result in such a massive split in behavior?
This brings us to a really crucial part of the source material, the concept of the spectral split, or spectral decomposition. The framework argues that while they stem from the exact same principle, they occupy entirely different modes within the closure spectrum.
Okay, let's use the spectral theory analogy here to break this down to the audience. We're essentially talking about Ising values, right?
Yes, think of any complex vibrating system, a drum head, a bell, or even an atom. You have specific, discrete, resonant frequencies, fundamental tones. In math, these are eigenmodes. They are sharp, distinct, and highly stable.
And in this framework, those sharp tones are the gauge forces.
Exactly. The gauge groups the math that governs electromagnetism and the nuclear forces. These are the discrete eigenattractors in the closure spectrum. They are deep, narrow mathematical wells of stability. Because they are discrete and tightly bound, they are hard. They interact strongly and sharply.
And gravity, how does it fit into the spectrum?
Gravity corresponds to what we call the continuum mode. In spectral theory, below or between those sharp, discrete eigenvalues, you often have a continuous, non-isolated band. It's a background hum that isn't isolated to one specific frequency, but is spread smoothly across the entire spectrum.
The source material specifically refers to this as hypergravity, or the partial closure substrate.
Right. Because it is a continuum mode, it is completely delocalized. It is spread out over the entire configuration space of the universe. And this is exactly what explains its apparent weakness.
Well, it's a dilution effect.
Exactly. The intrinsic energy of gravity is diluted across the infinite continuum, whereas the energy of the gauge forces is densely concentrated into these tight, discrete modes. That's why the coupling constants, the measure of their strength, are dozens of orders of magnitude apart.
So gravity isn't actually weak. It's everywhere all at once.
Yes.
And this must be the core reason why we completely fail every time we try to quantize it.
It provides a profound answer to the quantization problem. For half a century, we've been trying to force gravity into a discrete quantum box. We've been desperately hunting for the graviton, treating it as if it should just be another particle exactly like the photon or the gluon.
But if gravity fundamentally is the continuum mode, then trying to discretize it into a point particle is basically a category error.
It's a massive category error.
It's like trying to count the number of individual waves in a perfectly static, completely full pool of water. You can easily count the discrete ripples on the surface, which would be the particles, but you can't count the water itself in that same way.
Precisely. The theory strongly suggests that the graviton, as a standard quantum point particle, simply doesn't exist. Or at the very least, if we want to define it, it behaves as a collective quasi-particle of the entire background, not as a fundamental, independent, discrete entity.
Which perfectly explains why renormalization fails when we apply it to gravity. You're trying to treat a non-compact, continuous background as if it were a compact, discrete object. The math just rebels.
The math throws up infinities because it's the wrong tool for the job.
I mean, that is a deeply satisfying explanation for the failure of the last 50 years of high-energy physics. We were looking for a specific note, but we were actually listening to the silence between the notes.
A slightly poetic way to phrase it, but scientifically accurate within this framework.
Okay, I want to pivot a bit to the numbers, because this is where the theory shifts from being a really nice philosophical idea to, wait, did this just mathematically predict the structure of the standard model?
The 138 cluster.
Yes. We need to talk about the rule of three. Standard physics tells us that the standard model is based on a specific symmetry group structure, U1 cross SU2 cross SU3, electromagnetism, the weak force, and the strong force. And in modern physics, we usually just accept this as an empirical, brute fact. We say that's just how the universe happens to be.
Right. In the standard model, those gauge groups are inputs. We observe them in colliders, so we manually write them into the Lagrangian equation. The model doesn't tell us why they are there.
But this closure physics framework claims to actually derive why it is exactly these three groups, and not, say, SU4 or SB6. And it all seems to come down to algebraic complexity and the cost of maintaining stability.
Think of the universe as a very strict accountant. We already established that its primary drive is to minimize the closure defect, but maintaining a complex, twisting symmetry group carries a literal mathematical metabolic cost in terms of closure.
And this cost is what the notes refer to as a joint Casimir scaling. Let's unpack that term for the listeners.
Sure. In the mathematics of Lie algebras, the Casimir is a specific operator that commutes with all the generators of the group. If you look at it in the adjoint representation, the numerical value of that Casimir essentially tells you how internally active or twisted the group is. And crucially, it scales with the dimension of the algebra.
So simply put, more complex math equals a higher energetic cost for the universe to maintain it.
Roughly speaking, yes. So let's look at the complexity ladder the universe has to climb. What is the absolutely simplest possible compact Lie algebra? It's U1.
Which has a dimension of 1, it's just a circle.
Exactly. The closure cost is practically negligible. It's incredibly easy to maintain.
And physically, that translates to electromagnetism. Which makes sense. It's ubiquitous, it has infinite range, it's everywhere.
Then we step up one rung. What is the simple non-abelian algebra? It's SU2. It has a dimension of 3. It represents the mathematics of angular momentum in 3 dimensions. The cost is higher than U1, but still relatively low.
And that corresponds to the weak nuclear force.
Correct. Now we step up one more time. We hit SU3, dimension of 8, the algebra of quarks and gluons, the strong force. The closure cost here is moderate. It is a stable configuration, but mathematically we are rapidly reaching a limit.
And this is where we hit the cliff. Because what comes logically after dimension 8?
Well, you might look at a group like G2, which has dimension 14, or SU4, which is dimension 15, or maybe SO5, which is dimension 10. But the jump in dimension, and more importantly, the specific jump in the adjoint Casimir value is absolutely massive.
It's not just a smooth linear slope of complexity, it's a sheer step function, a wall.
Correct. The theory mathematically demonstrates that there is a severe spectral gap right after SU3. The complexity cost for anything beyond dimension 8 is so incredibly high that it cannot form a stable, low-energy attractor basin. The universe essentially tries to form it, and the math says, I cannot afford the closure cost for this structure.
So these larger groups like SU4 or SU5, they are just priced out of the market entirely.
They are inherently unstable in the low-energy regime. If they form at all, they immediately decay or are relegated to the extreme energies of the Planck scale. This natural cutoff creates the 1-3-8 cluster. The universe simply settles into the first three available valleys of stability and can't climb out to reach the higher ones.
I mean, this directly challenges basically all grand unified theories, doesn't it? Because standard GUTs almost always assume there is some massive overarching group, like SU5 or SO10, that existed at the Big Bang and then shattered or broke down into the smaller groups we see today.
Yes, it completely flips the GUT paradigm. GUTs assume the massive group is the fundamental reality, and the 1-3-8 groups are just broken shards. Closure physics argues the exact opposite. It argues that 1, 3, and 8 are the only truly stable configurations from the ground up. They aren't shards of a broken vase. They are the only three cups that can actually hold water. SU5 was never there to begin with.
Which has absolutely massive implications for things like proton decay. Because standard SU5 grand unified theories famously predict that protons should eventually decay. The math says quarks can spontaneously turn into leptons by trading these incredibly massive X and Y bosons that are part of the SU5 family.
And we haven't seen proton decay. Experimentalists have been watching vast subterranean tanks of ultra-pure water for decades, looking for a single flash of light from a dying proton, and the proton appears to be stubbornly stable.
Right.
Closure physics predicts exactly that. It says the proton should be fundamentally stable because there is no overarching SU5 highway to allow that quark-to-lepton transition in the first place. The U1, SU2, and SU3 sectors are distinct, isolated attractors. They are not just broken pieces of a single giant mixing pot.
Okay, so let's summarize where we are. We have a fundamental mechanism, which is the drive for closure. We have a mathematical derivation, the variation of the base and fiber. And we have a selection principle for the forces, which is Casimir scaling. Now, I really want to go deeper. Let's move to section 5 of our outline, the ontology, the seed bridge.
This is where we leave the strictly calculable physics and enter the metaphysical implications. But it's important to note that it's a metaphysics entirely forced upon us by the math.
The source notes specifically mention a paradigm shift from symmetry is king to closure is king.
Think about the history of 20th century physics. It was completely dominated by the concept of symmetry. Emmy Noether proved her brilliant theorem showing that every continuous mathematical symmetry in nature leads directly to a conserved physical quantity. Translation symmetry gives momentum conservation. Time symmetry gives energy conservation.
Right, so we just assumed symmetry was the ultimate primary input of reality. We would invent a mathematical symmetry, plug it in, and see what particles fell out.
Exactly. But in this closure framework, symmetry is recast as an output.
Symmetry is just the stable shadow of closure.
Precisely. The universe doesn't inherently care about being beautifully symmetric. It only cares about being holonomically consistent. Symmetry just happens to be the mathematically most efficient and lowest cost way to maintain that consistency. It's a natural attractor state, not a fundamental law handed down from on high.
I really like the evolutionary ladder the source describes here, the conceptual evolution ladder. It puts this entire theory into a really clear historical context.
It is a beautiful logical progression. Step 1 was no ether consistency. We realized that global symmetry leads directly to conservation laws.
Right.
Step 2 was gauge consistency. We realized that demanding local phase invariance forces the existence of the interacting standard model, Yang-Mills theory.
And 3 was geometric consistency. Einstein realized that demanding coordinate invariance forces the existence of general relativity in curved spacetime. And now, step 4.
Closure consistency. We realized that demanding transport composition consistency requiring loops to close at the most fundamental level leads to the total unification of steps 2 and 3. It is the logical completion of the entire historical sequence. Physics is simply the process of demanding consistency at a deeper and deeper structural level.
And at the very absolute bottom of that, well, we find what the author calls the seed equation, 0 to the power of 0 equals 1.
Identity persistence from null support.
I mean, that sounds like a Zen koan. 0 to the power of 0.
It is deeply philosophical, but it's a symbolic representation of the origin of the dual bivector itself. Imagine the absolute void. No space, no time, no particles, no geometry, pure 0.
Okay, I'm picturing the void, absolute nothingness.
In that pure nothingness does the logical concept of identity exist. Is A equal to A?
I mean, logically speaking, yes. Even in absolute nothingness, the definition must still define itself. A is A.
That logical tautology is the one, the persistence of identity. The theory argues that even with null support, The sheer logical requirement of identity, the one, forces a mathematical structure to emerge, because you cannot have identity without a formal way to verify that identity.
And verifying identity requires moving information. It requires transport. You have to be able to check if A over here is still exactly the same A over there.
And as we established, transport requires a relation, a non-commutative generator. So the sheer unavoidable logical necessity of identity forces the emergence of the dual bivector. It forces the continuum mode into existence to act as the support for transport, and it forces the discrete modes into existence as the things being transported.
So gravity and light and matter aren't just arbitrary things that were randomly created at the Big Bang. They're absolute logical necessities. They literally have to exist for the universe to be logically consistent with its own existence.
The phrase I like to use is that existence is simply the mathematical solution to the problem of being. The universe, as we see it, is the only stable solution.
That creates a very, very different feeling about the universe you live in. It's not a random, chaotic accident of initial conditions. It's a necessary, inevitable structure. But, and here's where I have to play the skeptic for our listeners, is this just really beautiful, elegant math? Or is it actual testable physics?
For a theory to be science, we need predictions. We need falsifiability.
That is a completely fair and necessary question. If this is just a clever mathematical redescription of things we already know, it's philosophy. To be true physics, it must predict novel phenomena.
We already talked about proton decay. That's a big one. It predicts protons are fundamentally stable, unlike standard GUTs. What else does it predict?
The big one is what the framework calls coupling clustering.
Unpack that for us.
Okay, so standard grand unified theories operate on this profound hope that if we can just build a powerful enough particle collider, if we go to a high enough energy scale, like 10 to the 16 GeV, the varying strengths of the strong, weak, and electromagnetic forces will perfectly converge to a single unified point. Their coupling constants will cross at exactly the same energy level. The Great Convergence. It's the holy grail of collider physics.
We've been desperately hoping for it for decades. But the actual hard data coming out of the Large Hadron Collider suggests they might not perfectly converge. The running coupling lines seem to miss each other slightly. They don't form a perfect point. Standard theories try to fix this miss by inventing supersymmetry, adding a whole new suite of undiscovered particles to artificially bend the lines so they hit exactly.
But we haven't found a single trace of any CY particles either, despite looking for years.
Exactly. Closure physics steps in and says, stop trying to fix the lines. They shouldn't converge perfectly. Because they aren't, and never were, a single unified force. They are three distinct, mathematically separate stability basins. The theory specifically predicts spectral clustering, meaning the couplings will approach each other at high energies, but they will remain fundamentally distinct, spaced slightly apart according to those adjoint Casimir complexity costs we discussed earlier.
So a near miss in coupling unification isn't a failure. It's actually direct evidence for this theory.
Correct. It naturally predicts the slight messiness that we are actually observing in the data, rather than the artificial mathematical perfection we have been fantasizing about.
What about predictions regarding the nature of gravity itself?
That is the other major testable prediction. If this closure framework holds true, we will never, ever find a discrete graviton. We can build colliders the size of the solar system, and we will never see gravity behave like a standard quantum field. We will only ever see it behave as a semi-classical continuum limit.
So if we keep striking out on loop quantum gravity and string theory and all these attempts to quantize gravity with gravitons, we are actually accumulating experimental evidence for the continuum mode.
Precisely. The persistent silence from the quantum gravity sector is, in itself, the primary evidence.
How does this overall framework compare to the other big players in the field? We mentioned string theory earlier. String theory notoriously needs 10 or 11 dimensions just to make the math work without anomalies.
And it absolutely requires supersymmetry. Closure physics is strictly four-dimensional. It works entirely in the observable space-time we actually inhabit. It doesn't need to mathematically curl up 6 invisible extra dimensions to hide the equations.
That makes it incredibly assumption minimal.
Occam's razor heavily favors it. It uses the exact standard model groups we already know exist and the four-dimensional space-time we already experience. It just radically reorganizes their foundational hierarchy.
And what about loop quantum gravity?
Loop quantum gravity is much closer in spirit, certainly. It respects background independence. But LQG aggressively discretizes space into granular spin networks right from the start. Closure physics maintains the fundamentally smooth metric for gravity. It says the physical space itself is smooth. It's the relations and information moving within it that are quantized into discrete chunks.
It really seems to elegantly thread the needle between the two dominant camps.
It creates a structural bridge. It uses the continuous geometric tools of general relativity but populates them natively with the discrete algebraic tools of quantum mechanics.
Well, we're coming up on the end of the hour, and I'll be honest, my brain feels like it's been run through a particle accelerator.
Yeah.
Let's try to summarize this massive architectural rethink for everyone who stuck with us.
It is a vast amount of structural geometry to hold in one's head at once.
We started way down at the bottom with the dual bivector. The radical idea that the fundamental atom of reality isn't a physical particle, but a twist, a pure mathematical relation.
The minimal generator of reality.
We moved from there to the loop test. The idea that the universe is fundamentally obsessed with holonomic consistency. It desperately wants information loops to close seamlessly.
And the inevitable closure defect is exactly what we end up calling curvature or quantum force.
We saw the great mathematical derivation. You vary the internal fiber, you mathematically get Yang-Mills and the standard model. You vary the physical base, you get Einstein and general relativity. One functional principle, two conjugate physical outcomes.
Resolving the century-old conceptual conflict.
Then we explored the spectral split. Gravity is the vast, continuous ocean, while the quantum forces are the sharp, discrete waves on top of it.
It perfectly explains why gravity is phenomenologically so weak and utterly resists all attempts at point-particle quantization.
And finally, we solved the mystery of the rule of three. The universe is essentially cheap. It buys the dimension 1, 3, and 8 algebras because they are structurally stable and have a low closure cost. It completely ignores the expensive dimension 15 and 10 algebras.
The rigid law of adjoint Casimir scaling.
It really profoundly challenges the traditional reductionist view of science. We usually assume that smaller is always more fundamental. But this theory suggests that logical consistency is the ultimate fundamental layer.
That is precisely the key takeaway. We shouldn't be looking for the absolute smallest physical particle. We should be looking for the most structurally stable logic.
I just keep going back to that seed bridge concept. 0 to the power of 0 equals 1. The incredibly provocative idea that we exist solely because pure nothingness is logically unstable. That the bare concept of identity actively forces a physical universe to happen.
It's a strangely comforting thought when you really get down to it. We aren't an accident. We belong here. We are the stable solution to a logical equation that simply couldn't be left unsolved.
We are the solution. I think that is the absolutely perfect place to leave it for today. For everyone listening, I know this is a really heavy technical one. We threw a lot of intense jargon at you. Adjoint Casimirs, fiber bundles, covariant derivatives, holonomy.
But the core intuition to take away is simple. The fundamental nature of the world is relation.
Exactly. Don't worry at all if you can't solve the differential equations yourself. Just try to remember the mental picture. A universe constantly weaving itself together, trying its hardest to keep its mathematical story straight, balancing the tension between the smooth, continuous stage and the dancing, discrete actors.
And doing a remarkably beautiful job of it.
Thank you so much for walking us through this incredibly dense material. This honestly feels like one of those foundational theories we might look back on in 20 years and say, that was it. That was the turning point.
It certainly has the rigorous mathematical potential to be that turning point. Time and the eventual closure of future high-energy experiments will tell.
To our listeners, thanks as always for diving deep with us. Be sure to check the show notes for direct links to the original papers on closure physics and the minimal generator theorem. Keep questioning the background of everything. Keep checking your loops. We'll see you on the next deep dive.
Goodbye.
See ya.